Thanks a lot for attending this workshop and come to my presentation. My work is part of my master's thesis, and it would be quite easy to understand to all of you. This work was conducted by me, my fellow student Yuanyuan Zhang, my supervisor Tanvina Patel, and Odette Scharenborg. I'm glad that I have all of you here, so let's start. The first question is, what is a bias? What is a bias in my title? The bias is quantified as the absolute word error rate difference between the absolute word error rate difference between different groups that ASR tends to generate more accurate predictions on certain groups within the data set while making more errors on others. As deep learning becomes more and more widely used in ASR, researchers also started to pay attention to the unfairness the deep learning algorithms are subjected to, although DNNs are often considered a harbor of objectivity. The state-of-the-art ASR systems are built on the basis of deep neural networks. Therefore, the fairness concerns are also mounting in recent ASR-related studies. Various works have shown that speech variability due to gender, age, speech impairment, regional accents, racial disparities, and non-native accents lead to recognition accuracy gaps among speaker groups. And there are many reasons for these biases to occur, such as first, the imbalanced training data set, second, the mismatch between the test data and the training data, and the vocal characteristics of certain speak group, also the specific architectures and algorithms used during ASR system development. Not related work. As seen in the table displayed in the slide, the bias exists among different speaker groups. The average word error rate difference of the state-of-the-art Dutch ASR system is the biggest between native speakers and non-native speakers. As you can see, it's absolute 26.1% for Dutch speakers and 55.9% for non-native speakers in read speech, absolute 39.8% and 61.4% in HMI speech. Therefore, we will primarily focus on mitigating the bias, that is word error rate difference between native and non-native Dutch speech. This table comes from the work done by a postdoc who used to be in our research group. According to his findings, conventional hybrid DNN-HMM model is slightly less biased across gender, age, non-native accents, and native regional accents than the E2E architecture. And also TDNNF acoustic model is less biased compared with the TDNN BLSTM system, which has the lowest word error rate. Therefore, the baseline used in this research has a TDNNF acoustic model. To offset the bias brought by the lack of accented speech data, the methods widely adopted can be categorized into first, increasing the amount of non-native speech, and second, improving the learning efficiency of the model when learning from the limited non-native speech resources. And furthermore, the possible methods of increasing the amount of non-native speech could be data augmentation, synthesizing speech, etc., and the possible methods of improving the learning efficiency of the model when learning from the limited non-native speech resources could be transfer learning or pre-trained models. The architecture of ASRs is shown in this figure. As the methods adopted are data augmentation and transfer learning, the stages we will pay attention to are pre-processing and acoustic modeling. That is to say, we do data augmentation during pre-processing stage, and we do some training strategies when training an acoustic model. So that is the experimental setup. First, we have the insufficient data from the non-native Dutch speakers, and we want to do data efficient learning. So we do data augmentation and we do transfer learning. The data augmentation techniques adopted are speed perturbation, volume perturbation, and pitch shift. And within the scope of transfer learning, we tried fine-tuning and multitask learning. This is the architecture of the TDNF acoustic model. As you guys all know, TDNs are one-dimensional CNNs, and it performs relatively well and efficiently as acoustic models. Our baseline model is TDNF hybrid DNN HMN architecture built with codiform, which is illustrated in figure. The TDNF model consisted of 12 TDNF layers of dimension 1024 and was trained with a cross entropy loss function for 4 epochs. 100 dimensional I vectors are applied to the MFCC input feature for speak adoption purpose. And the training strategy, other than fine-tuning, we also tried multitask learning. During multitask learning, the system is trained for multiple tasks simultaneously using shared information. The idea is that this allows the model to exploit similarities and differences between the two tasks to create a model that is better able to generalize than models trained on only native Dutch speech data. So as for multitask learning, we treated the recognition task on Jasmine CGN as another language, but not really another language. It's only a accented no, not really accented, only non-native speech spoken by non-native speakers. But in multitask learning, we treated it as another task with shared phones, with native Dutch, which is included in the CGN dataset. So the datasets used are CGN and Jasmine CGN. CGN is a Dutch corpus containing native speech data spoken by adult speakers from the Netherlands and Flanders. And Jasmine CGN is an extension of CGN, which contains speech data spoken by native and non-native speakers from the Netherlands and Flanders. So for the training, we used CGN, and for the fine-tuning and multitask training, we used CGN and Jasmine CGN. And for testing purpose, we used non-native and native speech data from Jasmine CGN only. So the test sets, 5 sets of target data, which is Jasmine CGN data, consisting of both native and non-native Dutch, are created and used for testing the performance of in-domain training, fine-tuning, and multitask learning. There are 6 speakers, 3 males and 3 females per age group in the test set. Each one has 2 types of speech recordings: human-machine interactive, HMI speech, and read speech. And for native speakers whose home language is only Dutch without any second home language are chosen. And for non-native speakers, the mother languages are picked to be as inclusive as possible. Their mother languages include Turkish, Russian, English, Chinese, Persian, Arabic, Polish, Bini Ado, and Pashto. So here are the results. Within the in-domain experiments, which means taking both CGN data and Jasmine data as a whole, just feed them into the model and train them, we observed that the different data augmentation techniques, when applied alone, gave only little improvement in recognition performance for both the native and the non-native speakers, and a small deterioration when only volume perturbed data is applied. Applying all 3 data augmentation techniques, however, leads to a reduction in word error rate, and the lowest word error rate for both the native and non-native speaker groups, for both read speech and HMI speech. The lowest bias, I forgot to say that here is a RD denotes the word error rate for read speech, and the D denotes that the test set is from native Dutch speakers, and NN denotes non-native Dutch speakers. For H, it denotes HMI speech, and the B thing on the right denotes the bias, which is a word error rate difference. The lowest bias for HMI HMI speech is also obtained when using all three data augmentation techniques, while for race speech, the lowest bias was observed when volume put up data was added, and this is due to an increasing in word error rate for the native speech, which was larger than the increasing word error rate for the non-native accented speech. In general, race speech is better recognized than HMI speech, which is true for all speaker groups, irrespective of the data augmentation techniques applied.
So we're in the last 4 or 5 minutes. If you'd like to summarize, and then we'll go to questions.
Oh, okay. I will go briefly over all the other results. So this slide is about fine-tuned result. As we can say, the lowest bias comes when all the data augmentation techniques are applied. And this slide shows the results from multitask learning. And as we can say, pitch shifted adjustment data leads to the lowest bias in rate speech. But we can also observe that not mounting all the data augmentation techniques does not necessarily lead to the lowest word error rate or lowest bias. This is the results for all of them. The conclusions are simple. So could data augmentation help reduce the bias against non-native accented speech in ASR systems? The answer is yes. And could fine-tuning and multitask learning be effective in reducing bias against non-native accented speech when compared with standard training methods? The answer is also yes. So that's it. Thank you. And I guess we don't have time for questions.
So thank you. That was a great presentation. We started at 32, so we have a couple of minutes for questions. If anyone has questions, please feel free to go ahead and ask.
So any questions?
Can I ask a question about the non-native speech? Did you, I know it's hard to be able to get data, but did you have different proficiencies in non-nativeness or
Yeah.
put together?
Yeah, but I remember there are differences in proficiencies, but the previous work conducted by the postdoc in our research group showed that the proficiency of non-native speakers does not necessarily lead to a lower word error rate when recognizing their speech.
Okay, thank you.
We can perhaps take one more question if the audience has any.
Okay. If there's no questions, we can just move on to the next presenter.
That seems like it might be the case. So thank you, Yixuan, for your presentation.